Hello. This is concrete path delivering the superposition method for the deflection of beams. So this lecture is entirely designed to understand the superposition method and apply it to solve the problems for getting the slope and deflection of the beams. So we had some standard results. By using those standard results, we can superimpose the effects of different loadings or combined loadings on a beam, and we can get the net final deflection and slope. So this is your that superposition method. Superposition method. So we write that some. So we write when there are multiple loadings. When there are multiple loadings. Say we have some 10 to 15 that standard results. Those results will be we would be using those results, then combine the effects to get the final to get final theta final and delta final. So we have some standard results. Let's say you write that you have a cantilever beam subjected to point load at the end, so it gets deflected. Here is some theta and delta. We write that slope theta and that next one is your deflection delta. So we write length is L. We write that the slope equals to P L square by 2 EI, and deflection equals to PL cube by 3 EI. So similarly we have one more that beam is subjected to concentrated moment at the free end. So because of the clockwise moment, beam would lift upwards. So we write that moment equals this moment produces a slope of ml upon EI and a deflection of ml square by 2 EI. Similarly, we can have a UDL cantilever subjected to UDL throughout the entire length. So we write that slope equals to WL cube by 6 EI and your deflection WL4 by 8 EI. Then after that we have that uniformly varying load with peak at this fixed support and uniformly varying that W here. So we write that slope equals to WL cube by 24 EI and your deflection WL to the power 4 by 30 EI. Then after that we have that simply support beam subjected to UDL throughout the entire length. So we write that slope equals to, so it gets deflected by this. So slope is produced at the supports. So theta and delta is produced at the delta max, at the mid delta max. So we write theta at the ends equals to that WL to the power 4, WL to the power 3 by WL to the power 3 by 24 EI. Similar to what we got in this cantilever subjected to uniformly varying load, WL to the power 3 by 24 EI. So after that we have to get the maximum deflection. We write 5 by 384 WL to the power 4 by EI. So your deflection gets increased by that by a factor of L into some constant L. Then after that we have that simply support beam, a simply support beam subjected to that concentrated moment from one of the supports. When it gets subjected to a moment from one of the supports, say it gets deflected downwards, then we can write that here it is the theta near. We can write theta near, and it is, this one is theta far. So where the moment is applied, we call it theta near, and next one is your theta far. So we can write theta near equals to ml by 3ei. Where the moment is more, so we can say close to the support where the moment is applied, we can have more theta. So we can write ml by 3ei, and theta far we can have ml by 6ei. That's 1 by second of that 1 by second of that theta near. Similarly, we can have delta maximum. Delta maximum is at L by 3 from the next support. So this is your L by 3. This is delta max. So this one is your 2L by 3. So then that delta max equals to ml square by 9 root 3 ei. Yeah, this is L root 3. That is L root 3. Yeah, it's, I think, L by root 3. We can verify it later also. L by root 3, I think. So after that, you just keep it in a circle. Maybe we can cross check it later. L by root 3. Then after that, we got those results, and we have one more. Say that a simply support beam subjected to point load at A from one support and B from one support. So length is L total. So we can write delta equals to PA square B square upon 3EIL. PA square B square by 3EIL. If you substitute the value of A equals to L by 2 and B equals to L by 2, we can write PL square L square by 4 3EI into L. So we can write PL cube by 48 EI for simply support beam subjected to point load at the mid. And theta would be PL square by 16 EI. So we forgot that to write that. You had simply support beam P, this is L by 2, this is L by 2. We can write theta is your PL square by 16 EI, and delta you already calculated that, PL cube by 48 EI. Then after that, we have that simply support beam with uniformly varying load. This question we also calculated in the by using that method of Macaulay's method. There we got the values, value of, say, that was equals to, so we got some value that was some 11 by 20, that theta equals to 5 by 192. This is the theta at the supports. When this gets deflected, this one is the theta at the supports. So 5 by 192 WL to the power 3 by EI. Similarly, deflection equals to WL to the power 4 by 120 EI. So we also solved one question. Say when we applied a concentrated moment at the mid span in the simply support beam, length was L by 2 M. So the slope formed was like, in this part it was upwards, and in this part it was downwards. So we have that theta at the ends equals to same, theta 1 theta 2, theta 1 equals to theta 2, that equals to ml by 24 EI, and theta at the near support, here theta at the near support, theta equals to ml by 12 EI. Then we have one more, say a fixed beam supported. That is fixed beam means it is fixed at both ends. So when it is subjected to point load at both ends, at A here and B here, we can write your delta equals to PA cube, delta equals to PA cube B cube by 3EI L cube. So if we substitute the value L by 2, we can get that P PL cube by 192 EI, PL cube by 192 EI. So when you have that simply support beam, we got that when we have simply support beam subjected to point load, we got the value as PL cube by 48 EI. So that the deflection here is PL cube by 48 EI, and here we got PL cube by 192 EI. That's equals to 1 by 4th of PL cube by 48 EI. So it's 1 by 4th of that simply support beam. So since fixed beam is that it's indeterminate structure, so your deflections get reduced. Say in this beam you got 1 by that 25% only deflection is produced. Similarly, you have a fixed beam subject to UDL throughout the entire span. So we get the deflection equals to, here the theta is 0 because it is fixed, and at the mids also theta is fixed and theta is 0 because your loading is symmetric. So there is no theta at the 3 critical points. Then we have that delta maximum equals to that WL to the power 4 by 384 EI. That's 1 by 5th of that delta simply support beam, that UDL with the UDL 1 by 5th. This was 5 times 3 by 84. So we can now solve some questions using these results. Let's say what question number 1 says that you have that cantilever beam, uniformly varying load, W at the free end and 0 at the fixed end. So we need to get the delta maximum and theta maximum. Since we can know that from at the free end, delta and theta would be maximum. Say this way. With the horizontal, from the horizontal there is a theta, clockwise theta, and your delta is downwards. So we can use the results that, since we know the result for the beam that's subjected to a uniformly varying load with maximum intensity at the fixed support and 0 at the free end. So this is one, the result for this one we know, and the result for the other one that we know also. Say this is also a beam subjected to UDL. Say UDL intensity of W, same UDL intensity of W. If we superimpose the two results, we can combine the two results. Say we can write that, say this one. Now we can also combine the two effects, that this is also UDL. The questions was that you had that the question was just this part that you got this one. We can have this in this fashion also, this way. So after combining, we can write that we have to see the net effect and how much deflection would be created. So for the we say that for this simply support beam, that for the cantilever subjected to uniformly distributed load throughout the entire span, we know delta maximum, say delta is maximum at the free end, delta delta equals to, we can write delta 1 equals to WL to the power 4 by 8 EI. And for the beam, for this beam that we also know that delta equals to delta 2, that equals to WL to the power 4 by 120 E into I. So but the result is that you don't have to add the both, because you only need a part, you only need this part, you only need this part. So this part, we can say, if you reverse this loading, this one, if you reverse the loading, it would become somewhat like this. So this is that part, so we have to subtract that part, so we can subtract that part. So we can write that delta final, delta net equals to WL to the power 4 by 8 EI minus WL to the power 4 by 120 EI. That equals to 11 by 120 WL to the power 4 by EI. So net value would be a downward value of 11 by 120 WL to the power 4 by EI. And next one is your theta value. So we can also write the equations. This results we have for the theta. We can write theta 1 we can have for the UDL, that for the UDL we know theta equals to WL to the power 3 by 6 EI, and minus, if we subtract theta 2 equals to, if we subtract the theta 2 is your that deflect slope for the beam, cantilever beam subjected to uniformly varying load with maximum intensity at the fixed support. So we have WL to the power 3 WL to the power 3 by 192 yeah, 24 EI. So we write that theta net equals to WL to the power 3 by 6 EI minus WL to the power 3 by 24 EI. So we get the value theta net comes out to be equals to that WL to the power 3 by 8 EI theta net. That's also clockwise. Then we have one more, say so this is your beam, that fixed beam, cantilever beam subjected to a point load P at A from one of the supports, and this part is your L minus A. Total length is L, this one is your L minus A, and this one is your A. So we need to get the delta maximum. We need to get the delta maximum. Say we can have we need to get the delta maximum. So this point we can say delta C, delta max, delta C, and theta C. This is your point C. So but the loading is such that after the length A, from A, you don't have any load after that. So if you write the shear force diagram, it would be like, say the reaction here would be P upwards, then after that it reaches to downward P here, then after that there is no shear force. Similarly, if you have bending moment, we can write that P into A is produced about point A. So clockwise moment of P into A. So here would be anti-clockwise moment of P into A developed, and it would be a linear variation till the point B, because area would be PA, and your load is minus, and your moment is minus PA. So after that there is no moment and there is no shear force. We have the standard result that curvature of the beam is M by EI. So if your curvature of the beam is say if the moment is not applied anywhere on the section, so here the moment is 0, we can write moment is 0 here. If the moment is 0, that means curvature is 0. Curvature if the curvature is 0, that means radius of curvature is infinite, or we can say it's a straight line. There won't be any deformations. No deformation in this part. No deformations. So if you want to make this, if you want to make the deflected shape of this part, we can say this was your load. Up to this point there would be deflection. Then after that we can have a constant slope, say this one, straight line. So we can have that here the theta would be theta A, and here the delta would be delta A, and the theta here would be clockwise theta A, clockwise theta A, clockwise theta A. So the same theta would be also present here, that this is also theta A. This is also theta A, and this is delta A, and this one would be this L minus A into theta A, because we have tan theta, because your slope sum is about that elastic limit, that 0.1 mm of that 100 mm bar. That means your tan theta is almost equals to theta, that equals to that L minus A by perpendicular by base. So we can get the values. So the result is that we can write, we have the standard result for that beams, cantilever beam subjected to point load at the free end. We have that PL cube by 3 EI, and theta is your PL square by 2 EI. So we can use the direct results here. We can write theta at the C, theta at C, this is your C. We can write theta at C equals to, this was your length A, this was the point load P. We can write PA cube by 3 EI. Up to this point, this is your delta at C. That's also called delta at A, 3 EI, PA cube by 3 EI. After that, you have to add, if you write that theta at A into your length L minus A, so we can write PA square by 2 EI. Then you have to multiply it with L minus A. So this is the result for the delta at C. So for the theta at C, we can write theta at C equals to theta at point load P, that equals to PA square by 2 EI. So your theta is a function of that moment in the section. If there is no moment, it would remain as a straight line. So you can write that. Now we can have a problem, say you got a cantilever beam. Now we have applied that UDL up to the point, that up to the length A, and this one is your L minus A, and loading intensity of W. So we can also say that again, that it would deflect downwards. Then after that, because your shear force is constant, because your shear force is 0 and bending moment is not there, that means a straight line would be there. So we can join the 2 points. So this part is a we can write that. For this result, for this part, we can have the result that So if you want to get the delta maximum, delta at C, that we can write that WA to the power 4 by 8 EI, that's delta 1, and after that there is a theta also, this theta. If you multiply it with your length L minus A, plus we can write that theta for the UDL on the cantilever, we can write that WA cube by 6 EI into your L minus A. Similarly, you can write that theta at the C equals to theta, that's equals to theta at the end of the load, that is WA cube by 6 EI. Now we can use the same question, but you can have the loading such that it's now the loading is on the part that W is acting for L minus A, and this part is your A. So now if you want to see now whether there is a straight line or not, we can show it by your shear forces and bending moments. Say the total shear force, say the reaction here would be W into L minus A, because only one support, and it would give a reaction of W into L minus A. Thereafter there is no loadings, though that means your shear force diagram is constant up to that point. After that your there would be a linear variation downwards. Since your loading intensity is constant, so your shear force slope is also constant, and your loading intensity is downwards, that means your slope is also downwards. So we got the shear force. Once you got the shear force, there would be bending moment. So if you want to say what is the bending moment, say here is some bending moment W into L minus A, then it's acting at the centroid, we can write that L, then after that you have L minus A by 2 plus A. So this is your some value of bending moment. Then after that it would linearly increase to say some point value here, some value of something value. Then after that it had to go by 2-degree curve, but that means your moment is there also. So at each part, so we can write at each part there is moment, at each section there is moment is there, so curvature is also there. That means your theta and delta is there. That means no there won't be a straight line, but say a curve is formed at every point. So we can now solve that. Say so, but the thing is that we don't know the results. We don't know the results for these. So we can do one thing. We can either go this way, then subtract this part as we did in Macaulay's method. Then in this part we know that result we already calculated by using this result. So this one is your one method. Next method is your, say you take the same loading. Now it was acting for W, this was acting for L minus A. So if you want to that we say that transferring, if you want to transfer these effects, transferring effect, that loads and moments are transferred to the next part. If you want to say what is the moments created at the end of this loading, so we can write W into L minus A. So here the shear force would be W into L minus A. Shear force would be W into L minus A, and a moment of anti-clockwise, that W into L minus A whole square by 2. So this one, next one is your now these two loads are transferred to the point for these would be transferred on this part. Say shear force was acting upwards, here the shear force would be acting downwards with some value that W into L minus A, and the moment here was anti-clockwise, so here the moment would be clockwise moment of WL minus A whole square by 2. So now we know that we know the results for these. So if say if a clockwise moment of if a anti-clockwise moment is acting at the free end of the cantilever, so it would try to deflect it downwards. So also the point load is also acting, it will also try to deflect it downwards. So we can have the both acting downwards, so we can sum the two effects. So we can write that delta 1 equals to that moment WL minus A whole square by 2 into length. This length was your A, so we can write ML square by 2 EI, ML square by 2 EI, ML square by 2 EI. And after that we can also add next one, that is because of that point load. This is your point load. We can write point load into A cube by 3 EI. So this one is your delta 1. But we also have the loading in this part also. We also have loading in this part also. We can treat it as a imaginary beam, that cantilever, imaginary cantilever beam subjected to UDL for intensity of W for length of L minus A. So your delta is delta 2 equals to W L minus A to the power 4 by 8 EI. Because see, as we transfer the effects, say this was your A, this was your L minus A. So we said that we have transferred the effects from UDL to point load here, point load P, and moment here M. So we say that there would be that a curve will be formed here. So if we want to calculate for this part only, we can say after that there will be a slope that is constant. The slope would be constant, and so we can write that we calculated for the delta 1. This was your delta 1. This was your delta 1. This was your delta 1. So delta 3 is also created there. Delta 3 is also created there. So we have to calculate delta 3 also. Delta 3 equals to that that slope here. So we need to get the slope because of these two loads. So slope because of these two loads, we can write W into L minus A. Point load is acting. A point load is acting, and we have the equation WL square PL square by 2 EI. PL square by 2 EI. PL square by 2 EI. Then we have PL square by 2 EI. Then we have plus moment because of the moment WL minus A whole square by 2. This is your moment, and length is A by EI. So we got the results. So this was your theta. Actually, this was your theta for the 3. So we can write delta 3 equals to, so once we got the theta 3, we can write delta 3 equals to length L minus A into your theta 3. So this is your theta 3, that theta 3 into that length L minus A tan theta. So we got the two results. But this was the case when there was no loading in the part L minus A. If there was no load in this part L minus A, but the loading is also there. So there is also moment. When we check it, there is a moment developed here because shear force and bending moment is developed here. So if the moment is developed, it can't be just a straight line. That it can't be a straight line only. It has to deflect more. So because of the this delta 3 is because we can write delta 3 is because of the effect of part A. That part A, because of the effect of part A, it deflected by an amount of delta 1, and it also showed a theta 3. Then if there is a theta 3 to maintain the continuity of the member, that since there was no moment in this part, it would follow a straight line after that. So the delta 3 is formed because of the effect of deformations in A, because of that theta 3 in A. Then there is actually a loading also. There's actually a loading also in this part, so we can write for that part also. We can get use that. We write that imaginary beam, imaginary fixed beam, imaginary fixed beam calculation. So we said that there is some fixed beam here because a moment is developed here and a shear force is also there, so we can treat it as a fixed beam. So for that you got delta 3. So if you want to say final that, say if you want to make the final deflection profile, we can have understanding in this way. Say this deflected by an amount of delta 1. So this was your delta 1. So this was your delta 1, and this was theta 3. We write that that theta 3. Then after that it had to remain as slope, that was a constant slope. Then there was a slope that was constant. Then we introduced a imaginary beam. So because of that effect there was some more deflection. It can't remain straight, it would deflect by some amount of delta 2. So this was your delta 3. Delta 3 equals to theta 3 into L minus A, and this was your delta 2, delta 1. So final deflection at the end support at the free end was your delta 1 plus delta 2 plus delta 3. So we treated it in this way, that we say that this was your loading configuration. For the theta 3 theta 2, we write that this was your theta 2, and imaginary beam, imaginary fixed beam. So next one is that you have that cantilever beam. You have the cantilever beam. So its cross sectional area is such that then its moment of inertia becomes I. So it has a moment of inertia I. So now you apply a point load here, point load of P. Now you need to get the delta at C and theta at C. Say this was your beam, point load here, and theta, this was your point C. You need to get the theta C and delta C. So this is length A, this is L minus A. So we know the result of that. Point load is acting at the free end. Deflection profile is somewhat this one. So we need to get the delta C and theta C. Delta C and theta C. So this is your clockwise theta C, and this is your delta C. So but the result is that we don't know the value here exactly. We don't know the value at this point. So if you transfer the effect to that, if you transfer the effect, we can make it in this way. We can transfer directly, but I am showing that if you cut the section at C, how can you transfer the force? So say this was your point P, this was length L minus A. Here the shear force would be L minus that P, value of P. Then after that there would be anti-clockwise moment of P into L minus A, because this effect is trying to rotate it in clockwise about that point, about that section C. So there would be anti-clockwise moment P into L minus A. So same forces will be transferred to this part. Say this is your moment P into L minus A, and your shear force downwards P. So we can write, we know the deflection profile for this part. So we got delta 1 and theta 1. So delta 1 is your PA cube by 3EI, and plus, because of the moment, that moment P into L minus A, ML square by 2EI. So we got the delta 1. Theta 1 we can get, the theta 1 would be PA square by 2EI plus moment ml by 2 ei ml ml by ei ml by ei. So we got the theta 1 and delta 1. So after that we can write delta 3 this is because of straight line, because of that straight line, that equals to theta 1 into your length L minus a. Then after that, because we already show you that this one, because of this effect, it will deflect this one, then it will go downward by straight line, because shear force and bending moment here would be 0. Delta 3 equals to theta 1 into L minus a. So we got the theta 1 into L minus a also. So you have to multiply it with L minus 1, L minus a. Then after that we have because the loading is in this part also. So there is shear force and bending moment also in this part. So if you write shear force and bending moment in this part, you have that this is your shear force for the entire section. Then bending moment is also there. In the part that C to free end, there is a bending moment. So bending moment is there. C to free. So we can write curvature is there. That means straight, and that means we can write curved path. So finally we can treat it as a, this part we can treat as an imaginary beam. If we treat it as an imaginary beam, say the moments, say treat it as a fixed beam, here the fixed moment is also there and shear force is also there. So it's like a fixed beam. So we can write it, the load is acting P and length is L minus a. So we can get delta 2 equals to this way, PL minus a, PL cube by 3 ei, PL cube by 3 ei. Similarly we can write theta 2 here, that's PL minus a, PL square by 2 ei. So the final diagram would be look like that, this way. So we need to get the theta at this point. So this was your point C. We need to get delta C and theta C. So initially we got that here the deflection profile was somewhat this way. Then after that it remained constant. Then it deflected by amount of delta 3, delta 2, and slope also changed. So final slope here is theta 1 plus theta 2, final slope. And if you want to say what is the theta 2 here, the theta c, we can write theta c equals to, we already calculated that as theta 1, and delta 1 equals to, we already calculated that. There was no need to calculate the extra part, that delta 3 and delta 2. We only need to calculate delta 1 and theta 1, that are the deflection and slope at the point C. So we only needed to calculate this part. This part we only needed to calculate delta 1 and theta 1, that delta 1 equals to the delta C and theta 1 equals to theta C. So similarly we can have one more problem. Say you got a beam such that its moment of inertia changes from I to 2i for length L by 2, and after that there is also L by 2. So you have L by 2 and you have L by 2. Here the moment of inertia is 2i and there it's I. So and the point load P is acting at the free end. Point P is acting at the free end. So you need to get the value of, say this is your point C. You need to get delta C, theta C, and delta B. So this is your point B. So here the thing is that your EI also changes. That I changes, that means you have to account that also. Let's say let's treat it as a straight line, that we can get a better understanding. Say for the theta c you have to transfer the effect. For the theta c you have to see what is the deflection at this point. For that you have to transfer the effect of this part. So we can transfer, we can write theta c. For the theta c we can transfer the effect that this was your point load P acting here. We need to get delta c here. It's L by 2. This is L by 2. We need to get at the C. So if you transfer the forces, and if and the final diagram would look like that. Say the point load would be here P, and a clockwise moment of P into L minus P into L by 2. That I show how you can draw the free body diagram, that P and this one. Similarly you can transfer the effectors. So we got the results that for this we know that results, say deflectors by amount of delta c and theta c. So after that the slope remains constant. So this was the case for the pure, if there was no loading in the part CB, but the CB is also having some load. So you can have that CB is also having some load. So CB is also having some load. You can write plus CB is also having some load, point load here acting at the end. So you can get delta next. So final delta would be, delta at B would be, say, delta 1, delta 2, and delta 3. So delta B equals to delta 1 plus delta 2 plus delta 3. So delta 1 is your delta C. Delta 1 is your delta C plus theta C into length L by 2 plus theta 3. So we need to get the value of theta C and delta C. Theta C and delta C is easy. If you try, say theta C, we can write theta C equals to ml, that PL square by 2EI, PL square by 2EI. Your I, you have to see what is the value of I in this part. This is 2I, this is I. So PL square by 2EI. Then after that plus, because of the moment, this is your moment M, ML, ML by EI. E into I is the value of 2I. So after that delta C is delta 1. So we can write PL cube by 3EI plus P, this is your moment M, ML square by 2EI. Then you get the value of theta C and delta C. Similarly, you can write delta 2 equals that theta C into L by 2. And similarly, you can write theta 3, that equals to theta 3 equals to that value of P L cube by 3EI. If you want to say what is the value of theta B also, you can say theta B is also equals to, say the final profile would be somewhat this way. So we can say theta B is final, theta B equals to theta C plus that PL square by 2EI, PL square by 2EI. But your L is equals to L by 2, PL square by 2EI for this part. And you have to check also what is the value of I in each of the span. So then you can add these results. Final results would be, say, you got a value of delta B, that equals to 3 by 16. No, delta C, yeah, delta B equals to 3 by 16 PL cube by EI downwards, and you got theta C equals to 3 by 16 PL square by EI, and you got delta C equals to 5 by 96 PL cube by EI. Now we can have that. So we said that this was your imaginary beam here. So after that we can have problem of, say, there is an overhang also. A point load is acting at the overhang free end. This is your point load P. This is a support. This is your point C. Support roller at B, at L, at A from supports at A from point load A. That point load. This is your I, and this is your also I. That means I is constant and length is L. There is a hinge support A. We need to get the value of delta and theta at C. We need to get the value of theta and delta at C. 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 So we can say, so how can we solve that? If you want to make the shear force and bending moment diagram, you can see what should be the variation. Is there any straight line? Because say you can now directly say, if this part, this part, in this there is a shear in this there is a load acting, so there is some curvature. Because of that there would be some deflection, and we know that if there is if it is going downwards, if the span BC is going downwards, this part has to go upwards. It has to go upwards to maintain the slope. If there would have been some external load here, it would have deflected downwards. Then after that it would have made that slope here and here same. Then also it would deflect downwards here. But loading is not there in the span AB, so it can go in an easy manner that it can go upwards. Say this was your slope, it can remain constant this way. So we can write there is some theta. We have to see that if there is any effect of AB on BC, as we saw earlier, that if there is some theta, it might rotate downwards if there was no load P. So we need to transfer the forces. So we can transfer the forces. So if we want to transfer the forces, we can actually calculate the shear that reactions, or we can do one thing. We can transfer the effect of P on the support B. Let's say we are transferring the effect of point load P on the support B. So this is your shear force here, that equals to P, and here the moment developed would be anti-clockwise P into A, and same moment would be transferred to the support B. You are cutting just to the that right of the support B. Let's say this same value of for that moment would be transferred in the clockwise direction, in the clockwise direction. If this is anti-clock, that means it has to be a clockwise moment. So this was your clockwise moment, P into A, and a shear force of that P downwards. Say we can say, what is the effect of this P on the support B? Say this is your beam. It has a point load acting at exactly at the point B. Say you can say the shear forces and bending moments diagrams would look like that. This is your shear force diagram. Say here the load was acting downwards P. Here it the reaction is also P. So the final value of shear force here is 0, and entire span it's also 0. If you calculate that reaction from moment equilibrium, or you can say from the result of that PB by L, your value of B is 0. You can do that. So you got the reaction. So we can say here the reaction is also P, here the reaction is 0. If the reaction here is 0, it would remain straight. Then after that you got a downward load of P. Then after that you got still sudden upward load of P reaction. So finally you have that shear force diagram equals to 0, and there is no bending moment, so we can have bending moment also 0. So we can say there is no effect of this point load in the deflection profile. There is no effect of this point load. it gets directly transferred to the support B. There is no effect of this one on the deflection profile. That's no effect on deflection profile. And now we have that concept there. Say this beam, because of this moment that's acting to say this is a beam, this acting moment is acting in the clockwise direction. If the moment is acting clockwise direction, so beam would but the beam is such that it is a simply support beam. If the beam is simply support beam, if the moment is applied, so it would not go, and at the end it would not deflect. So but it would go upwards, say this way. You are applying a clockwise moment, so it would deflect upwards. So it would deflect upwards. So it would deflect upwards. Say this is the deflection here. The theta is some theta b. So after that it would remain constant, because in this part, say, because we are saying that there was no moment, there was no load acting in the part as BC. So we can treat that separately. Say you can have this part, say there was a point load P, and after that there was that, we can say, we can join them by straight line there. Say this, in this part there is no shear force and bending moment, no shear force and no bending moment. Because there is no shear force, there won't be any bending moment. If there is no bending moment, there won't be any curvature. So it's a straight line. So you have to join that. It is a straight line. So here the delta would be delta here would be equals to theta b into your length of A. So this is your deflection at this point, because if there was no load acting in the span BC, but there is a load acting in the span BC, so we can show that as that of a imaginary beam fixed at the support, because there was that moment of P into A developed at this point and shear force. So we can treat it as a imaginary beam. You apply load P here, it gets deflected by an amount of PA cube by 3 EI and slope of PA square by 2 EI. So the final deflection profile would be somewhat say this one at the top. We can remove this one. So if you want to make the final deflection profile, it would be like, say, this way. Then after that a straight line. Then after that a deflection downwards. So the final theta here would be that theta at B. So theta at B plus theta this one theta 2, and this is delta 2. Here the deflection is equals to theta at B into length A plus and your this value of delta 2. So we can say what is the value of effect of this moment at this. So we can write what is the value of theta b. We wrote the equation for the that if there is a simply support beam and concentrated moment is applied at one of the supports, so the theta at the near equals to ml by 3 ei, and theta far is ml by 6 ei. So theta b we can write m into l by 3 ei, and we can say what is the value of this one. We can write it is equals to PAL by 3 ei into A. So we can then add the final values, that what is the value of theta b. Theta at the B equals to PAL by 3 ei plus that value of PA square by 2 ei. PAL by 3 ei, PA square by 2 ei. And similarly we can write delta B equals to this value BA square L by 3 ei plus and next one of PA cube by 3 ei. Now we have one more. Because of this superposition, we can also solve indeterminate problems also. Say this is a proper cantilever of length L subject to the UDL of W throughout the length. This is your support B. Let's say the reaction here is B, and moments we know there would be MA and VA shear force. We need to get the value of theta B, and we need to get the value of shear force at B, or reaction at B. We can write reaction at B. So the deflection profile, we know already that here the theta and delta is 0. Then after that it would go downwards, and the delta at B, we know that compatibility condition we can use. Compatibility condition that delta at B equals to 0. It has to be 0 because your support is there, so your delta is 0, but it is a free that roller support, that means your theta is possible. Theta is possible at B. So initially, if we get the value of reaction at B, we can then get the value of theta at B. So we can use the compatibility condition. Say we can write it as a structure which is having a which is a cantilever subjected to a uniformly low UDL that for the entire span. So the deflection profile is somewhat downwards. So the theta is anti-clockwise theta of WL to the power 3 by 6 EI, and a deflection of WL to the power 4 by 8 EI. And we can also say there is fixed that cantilever beam subjected to a point load of reaction B, so it would go deflect, if it would deflect upwards. Say the theta here is anti-clockwise. Here it was clockwise theta. Theta was clockwise. Here the theta is anti-clockwise from the horizontal axis. So theta here is BL cube by 3EI. Now this is your delta. Delta is your BL cube by 3EI, and theta is your B or BL square by 2EI. So one is clockwise, next one is your anti-clockwise, and delta in this span is downwards, and in this part, because of the effect of B, it's upwards. So we have to subtract the values. So we can have the compatibility condition that delta B equals to 0, that equals to delta B 1 plus delta B2. So we can write WL to the power 4 by 8 EI. We can show that our arrow it's acting downwards, and you have to subtract it by that BL cube by 3 EI. It's acting upwards. That's why you are subtracting the value. Or you can add them. Then you have to say the sign that upward is say positive or negative. It's up to you. Then after that, you have to equate it with 0. We can get the value of B equals to 3 by 8 of W into L. So the reaction, we got 3 by 8 of W into L. And you can get similarly the value reaction at A. So the reaction at A would be reaction at A equals to W into L minus 3 by 8 of WL. That equals to 5 by 8 of WL. So the shear force diagram would be like this is 5 by 8, this is 5 by 8, and this is 3 by 8 upwards. So the slope is constant, that means a straight line. So this is your 5 by 8 WL, 3 by 8 WL minus plus, you can get the value of X where the it's cutting, so we can get the value. At that point there would be maximum bending moment. We can have here bending moment that is maximum. Say if you want to say what is the value of bending moment at the end span, we can say bending moment here would be developed equals to W into L, total load of W into L. It's acting at the centroid at L by 2 from the support A, WL square by 2. No, this was the case for cantilever beam, but here is the reaction also. So we can do the summation of moments at A equals to 0. If you say summation of moments at A equals to 0, you can write that reaction B is acting anti-clockwise about A, and your UDL of that WL square by 2, and moment we have assumed that moment is acting anti-clockwise, so we can write moment A equals to 0. Then we can get value of moment A equals to value of B was 3 by 8 WL, and into L minus WL square by 2. So we can get the value as 3 by 8 plus 2 inverse. Is it correct? 3 by 8 WL by 2 WL square by 2. Moment WL square by 8. What is the issue here? Reaction of 3 by 8 of WL, 3 by 8 of W into L into L, and clockwise WL square by 8. Yeah, it says this was your anti-clock, and this was your clockwise. So it was positive and this was negative. So this was your minus and this was your plus. You get a value of WL square by 8. WL square by 8 downwards, because you assumed that direction is anti-clockwise, so WL square by 8. And we have to see what is the value of moment here. So we can write that we don't know the value here, so we can get the value here summation by that similar triangles, that equals to 5 by 8 L, because WL by 8 is changing in length x, and it changes to 3 by 8 WL in length L minus x. You can get value of x equals to 5 by 8 of L. When you substitute value here, you can say what is the area of the SFD. We can write 1 by 2 WL by 8 into length 5 into L by 8. You get the value, some value. You add with this one negative value of WL square by 8, and you get a value here that equals to 9 by 128 WL square. So you have to join that, because your shear force here is 0. Your shear force is 0. That means your slope is maximum. Yeah, your value is maximum, and your slope here is 0, because shear force is 0. That is slope is 0. And joined by 2-degree curve, and after that the slope here would be 0 if you check by that area of the SFD also. So it cuts at this point. Let's say it cuts at x from support A. Here the moment was WL square by 8, and the reaction was upwards 5 by 8 of WL, and this is your length x, and here the shear is V. We don't care about the shear. We say what is the moment at x. We say that bending moment at x is 0, and also we have that bending moment. We have that result of that summation of moments at x equals to 0, and we know that mx is acting anti-clockwise direction. That mx is your bending moment at x, and you have the UDL acting also anti-clockwise WX square by 2. You also have anti-clockwise WL square by 8. You have positive 5 by 8 of WL equals to 0, and your moment at x is also 0. That's point of counterflexure. So we can get the value of x equals to x value equals to 0.25 L. At this point, 0.25 L. So once we got that critical point, we can make the deflected shape. So this was your UDL acting for the entire span, and this was your that proper cantilever. At the point of counterflexure, there would be a point of inflection in the deflected shape. See, up to this point there was negative moment, so your hogging moment was there, hogging curvature. So we can write hogging curvature. Then after that there was change in curvature, so we can write in this fashion. This is your hogging, this is your sagging. So this was your point of contraflexion and point of inflection, point of contraflexion. So we have to get the theta c, theta at this support b. So for that we have to add the two effects that we got. We say theta b would be equals to, here the theta was because of this load, theta was WL cube by 6 EI clockwise, and because of the reaction B, you had theta B equals to BL square by 6 EI. It was anti-clockwise. Final, we can see from the diagram that final value is acting anti-clockwise. So effect of that, effect of B is more. If you say what if you say that WL cube by 6 EI, you have to subtract it by BL cube, BL square by WL cube by 6 EI minus BL square by 2 EI. So we would say what's the net value. If you say let's subtract that BL square by 2 EI from WL cube by 6 EI, we would see whether the value is negative or positive. Let's say WL cube by 6 EI, and your reaction was 3 by 8 of W into L, and you have L square by 2 EI. So you get value of reaction B, that theta B equals to WL cube by 48 EI. So you got a value that is negative. Finally you got a value that is negative. That negative means this was acting clockwise. This one WL cube by 6 EI was acting clockwise, and this one was acting anti-clockwise. If your value is finally negative, that means this value is more, that means anti-clockwise is more. So final value would be anti-clockwise, that we already saw in this shape also, that it is anti-clockwise net WL cube by 48 EI. So we have one more problem. Say this is your fixed beam subjected to point load at the midspan. This is your P and L by 2, L by 2. We know that loading is symmetric. If loading is symmetric, your deflection profile is symmetric, and delta is at maximum. Delta maximum is at mid. If delta is maximum at the mid, your theta is 0 at the midspan, because your shear force is 0 at the midspan. Is 0 at the midspan. Your bending moment is maximum at the midspan. Your bending moment slope is also that 0 there. Bending moment slope is also bending moment slope is 0 because shear force is 0. So because of that curvature would be that horizontal theta. So the deflection profile would be somewhat like this. So we can use the compatibility, or we can to get the value of, we have to get the value of delta maximum. We have to get the value of delta maximum. So at the value of delta maximum there is theta that is 0. So we can write at theta maximum, at theta delta maximum, that theta is 0. Theta is 0. This is your condition. You have to make the theta 0 at the midspan also. So for that, if you say let's cut the section, since your that structure is symmetric, you can cut the sections as such that the loads are balanced in both the spans. Say you cut the section that this was your point load P. Now say here the direction, it would be upwards P by 2, and here it would be also P by 2, because your structure is symmetric, so it takes the load equally. So then you transfer these effects on this part. So this is your P by 2, and this one is your P by 2. And this one is your length. This one is your length L by 2. Then if I solve that, I would say P L cube by 3 EI. say 2004 to 1648. We know that let's say as of now there's no you see that there is no moment developed, but if you analyze that structure in the indeterminate structures, here the moment developed is PL by 8, then you have some moment here, there is some moment developed, but we don't know the value here moment. Some moment is developed at the midspan. Because of that, we have that shear force is 0 there, and bending moment is maximum there. We have to see what is the value of moment here. Say the bending moment here is that is positive. Say that is positive. If you write that here the moment is m, here the moment is acting m, here the moment is acting in this span clockwise, and yeah, opposite that. Say here the moment is m, and here the moment is m. So we can use that in this part. It's one of the parts we can use that. Say we have to ensure that theta is 0 at the midspan. How can you make the theta 0? If only point load was acting at the span, how can theta be 0? So there should be some moment that's acting anti-clockwise direction. Say moment m is acting anti-clockwise such that it lifts the beam upwards also to make this theta 0. So there is some moment developed that theta anti-clockwise moment that tries to lift it upwards such that theta becomes 0. So we have that two effects. Then we have plus that this one moment acting anti-clockwise, it tries to lift it upwards such that the final theta here should be 0. So if we write the condition for that, we have to make this theta 0. So we can write theta equals to p, but the reaction is here that reaction is p by 2, because it only half of the load is transferred to one part of the beam. So p by 2 length is also l by 2, pl cube, pl square by 2 ei, and because of this there is upward moment. So this was your clockwise theta was clockwise, and because of this theta is anti-clockwise theta. So we write because of this moment m, we don't know the value of m, we say theta 2 equals to m l by ei. So we have the that condition or compatibility that theta mid equals to 0, that equals to p by 2 l square by 4, and you have 2 ei, and you have m l by 2 ei. So you have to say if it is your clockwise, this has to be anti-clockwise, so you have to subtract the two values. So you get the value and that equals to 0. That means your moment comes out to be equals to pl by 8. So a moment of pl by 8 is also there. So this is a special case that if the beam is fixed and point load is acting at the midspan, you get a moment negative moment of pl by 8, and you get a positive moment of pl by 8. Everywhere you got pl by 8. Here is also pl by 8, pl by 8, and pl by 8. So once you got the value of pl by 8, you had to get the delta maximum. So you can get the delta maximum. Now we can get the delta maximum, that's difference of the two values. So we can have the difference of the two values. Say first one, because of the, we can write delta 1 was your p by 2 l cube pl cube by 3 ei, and you have to get the delta 2, that's upwards. So you can keep downwards positive. So a sign convention is just that you have to see whether which one is, say, positive and subtract that negative, so that final value should be that summation of those values. It should not be such that you add for the terms which should have been subtracted. So that's why that sign convention is necessary at that time. So we know that from the that figure and analysis we can get the idea that which one is going upwards and which one going downwards. So delta 2 is going upwards, so we can write moment was m into L square, ml square by 2 ei. So you can get the delta net at mid, delta net at mid equals to, that comes out to be equals to PL cube by 192 ei. That we have already shown you in the standard results, that it was equals to PL cube by 48, that 1/4 of PL cube by 48 ei. For the simply support beam it was this one, and just 1/4 of that. And similarly you take now the problem that actually we have solved this part. We have solved this one. Yeah, we have solved this one. And after that, say now we also got this problem, a moment acting anti-clock in the clockwise direction at the end, at the free end. So you got this beam. You need to get the value of theta c delta c, theta c delta c, theta c and delta c. So this is your c. So we don't say we know that if the beam is this way and moment is acting, we know that theta and delta, but we don't know the value effect of this part. We have to see the effect of AB also. Effect of AB we have to check. Effect of AB. So for that we have to transfer the moments. Say we will transfer the moment. Say here the moment is acting M, and here it should be M because there's no one to balance it. It tries to, this external moment tries to rotate the point B in clockwise, so there would be a moment of anti-clockwise moment M then generated, and there is no shear force because no load is acting. So you got this moment M, and you have to transfer it to your support B. So because of this moment about point B, it would go upwards, and say there was no load in the span BC, so it would go straight downwards. So this is your theta equals to ml by 3 ei. This is your theta near, and this one is your ml square by 6 ei. We don't have to use this value, we have to get the theta b, that is ml by 3 ei, and this one, this delta here would be equals to theta into your length L by 2, this length L by 2. Then after that you have to use the imaginary beam concept, that this is your beam of length L by 2, and you are applying moment M. It deflects by amount of m L square by 2 ei, and theta of, say, theta equals to m L by ei, but your L is L by 2. So finally you can write the equation that delta at C equals to, so delta at C equals to, in this fashion we can say delta at C equals to theta b into L by 2 and this part delta C. So we can write delta C equals to theta b we got ml by 3 ei into your length of L by 2 plus, because of the effect of this imaginary beam, so we can write delta equals that delta second, that's m L square by 8 ei, ml square by 8 ei. So we got the value delta C. Finally we can write delta C equals to 7 by 24 ml square by ei. And similarly we can write theta at C equals to that theta at B, same is the theta at C, but it's deflected by imaginary beams by some amount, such that the final value becomes theta C equals to theta B plus that amount of this one ml by 2 ei, and this one was your ml by 3 ei. So you have to add them. So finally you get the value as 5 by 6 ml by EI. That's also anti-clockwise. That clockwise, sorry, clockwise. Now next one is your a good question that relates the two results that we saw earlier. See, UVL is acting for a length of 3 meter, and this one is your 2 meter, and say this one is your 3 meter, and intensity here is 6 kilonewton per meter, 6 kilonewton per meter, and similarly we have, so because of this there is delta 1 created, and we have one more beam, cantilever beam, and loading is same, but you have reversed the direction. So loading here is acting for 3 meter, here 6 kilonewton per meter intensity, so the length is 3 meter, and this one is 2 meter. Say there is delta 2. You need to get the value of delta 1 by delta 2. You need to get the value of delta 1 by delta 2. So we don't know the direct results. So we don't know the direct results. We have the results. Say the result we know that this result we know, and this result we know that when we calculated this result from this result using concept of this one. So but the thing is here, it's not continuous up to the support B, support fixed, support A. So we can make that, we can make use of imaginary beam concept and you're transferring the forces and plus transferring the forces. So let's say that the centroid of the UVL is acting at this part, and the centroid of this one is acting here. So you have to transfer the effect at this point, you have to transfer the effect at this point. So we can say, let's say it deflects downwards this one, then after that it remains straight, then because of that imaginary beam concept it will deflect downwards. Now similarly, let's say it deflects downwards, then it remains straight, then after that this one. So we can write that we have to transfer the effects. So if we transfer the effects, we can write, let's say this was your UVL for 3 meter. So here the shear force would be area of the triangle 1 by 2, 6 into 3, that's 9 kilonewton shear force upwards, and the moment here would be equals to, because of this UVL it tries to rotate about the point section X in the clockwise, so a moment of 9 into while it acts at 1 by 3rd of 3, that's 9 kilonewton meter. So a transfer of 9 kilonewton meter is developed. That if we want to make it now in a transfer mode, we can say a 9 kilonewton meter is acting, and a 9 kilonewton is also acting at this point. You have 3 meter free. So the deflection is like this one. Then after that, so we can write it delta 1, delta 2, delta 3. Let's take it as delta A, this one as delta B. So we write delta 1 we know, and delta 2 we know. We can say what's the value of delta 1. So delta 1 is your, so this length is your 2 meter. We can write delta 1 equals to PL cube, P is your 9, PL cube by 3 EI plus, because of the moment it's acting in the clockwise direction, so it tries to deflect it downwards. So your moment of ML square by 2 EI. Similarly, you get delta 2 equals to, here theta, you need to get the value of theta 1 into your length of 3. This is your delta 2. That's theta 1 into 3. theta 1 into 3. So theta 1 equals to PL square by 2EI, PL square by 2EI. This is your theta. So we can write theta PL square by 3, PL square PL square by 2EI plus M. M is 9L by EI, 9L by EI. So we get the value of theta 1, we can get the value of theta 2. So then after that we have imaginary beam concept. You have to make it in this way, that this is your third part, imaginary beam. So it deflects by amount of delta 3. So your delta 3 becomes equals to, we know the result for this case that we have WL to the power 4 by 8 EI, and we can use that. So we can write, is it WL by L to the power 4 by 8 EI? I think it's the same, WL to the power 4 by 8 EI. WL to the power 4 is for the UDL, and for the UVL you have 30. We have 30. It's 30. So we can write intensity here was 6, and 3 length is your 3 meter. We can write 6 into 3 to the power 4 by 30 EI. Then we can get the value of delta B, delta A equals to delta 1 plus delta 2 plus delta 3. So that comes out to be equals to 166.2 by EI. And now we have the case 2. Similarly, we can transfer the forces. Now we can transfer the forces. Say this is your 3 meter, 6, and centroid is here. Say the shear force is also same because loading area was same, that half of 6 into 3, half of 6 into 3, that's 9. Here the moment, say it's trying to rotate it clockwise, so moment will be generated anti-clockwise. So moment of that 9 into that the distance here is 2 by 3, 2 by third of 3, that's 18. So a moment of 18 is developed. In the first case, the moment of 9 was created. Moment of 9. That moment of 9. Here we have, because the lever arm changed, because of that 2 by third. First one was 1 by third. So you got 9, and here we got 18. So 18 is to be transferred, and a reaction of 9. So we can say it's your 2 meter. This is your 3 meter. A reaction of 9 and a moment of 18. So deflection this one, then straight. So this one is your delta 1. This is your delta 2 equals to theta 1 into 3. This is your theta 1. So we can write delta 1 equals to 9 9L square, 9L cube by 3i. Theta 1 is your, and we have to add the 2 because of the moment is also acting there. Delta 1 is your 9L cube by 3i plus, because of the moment, you have 18 ML square by 2ei, ML square by 2ei. So we have theta 1 equals to PL square by 2ei plus ML by ei, and we have that. So we can get the value of delta 2. So then after that we have the imaginary beam. So subjected to that load such that maximum is at the free end. So we know the result for that. Delta 3 equals to that. First one was your WL cube by 30, WL to the power 4 by 30 EI. And this one, the result we derived that it was something 20, WL to the power 4 by 120 EI. I guess this was the result. 11 by 120. 11 by 120. You have 11 by 120 EI. That 11 by 120, your loading intensity was 6 and length was 3 meter. So we can write 6 into 3 to the power 4 by EI. So we can get the value of delta B equals to delta 1 plus delta 2 plus delta 3. So that comes out to be equals to 266.55. So we can write delta A by delta B, that equals to 166.2 divided by 266.5. and EI gets cancelled, so we write 0.6235. Now we have the other problems also in this that in the superposition method. So we can erase the paths. So you got, let's say you have a fixed beam, but the thing is you also got internal hinge. You also got internal hinge at A from support A and at B from support B, and a load is acting on the internal hinge. A load of P, it's at C, so a load of P is also acting there. So we know that one condition for your internal hinge, that members rotate independently. Members rotate independently. So your theta 1 is not equals to theta 2, or it can be theta 1 equals to theta 2, but they rotate independently. Say that the theta developed here is, say, theta 1, and say theta 2 developed here is, say this one is your theta 2. It can't be equals to theta 1 is not, so we write that theta, it can be also equal to, so but we say that theta 1 and theta 2, it depends on the loading and configuration of those lengths A and B. So we write that theta 1 and theta B, but the main thing is compatibility here is, if delta 1 has to be equals to delta 2, because it is a joint. If one goes down, second one has to go down to maintain that structural member, to act as a structural member, to behave together. They should deflect by same amount. If member 1 is going down by amount of delta, second member has also go to down by same amount of delta. But the angle can be different. It depends on the length, and it depends on the configuration, that loading configuration. So let's say you cut the section. We want to see the forces. Let's say it's your hinge. We know that hinge in the bending, at the hinge, bending moment is 0, and it transfers only shear forces. It transfers shear force. Let's say point P is there, and we cut the section. Let's say that the reaction here is, let's say the reaction here is, let's say reaction here is V. Let's say reaction here is V. From this side, we can keep any side, but I have solved it from this side, such that I keep shear force V in this part. So here the shear force would be P minus V, isn't it? Shear force here would be P minus V. So in this part, in the span A, we can have shear force downwards, P minus V, and in this part we can have shear force downwards, V equals to V. So in one part we got P minus V, next part you got V. So we know that delta 1 equals to delta 2, so it deflects downwards. So we have that P minus V, A cubed by 3 EI, and it deflects downwards. So we have that VB cubed by 3 EI. For them to be equal, we equate them. Say we get the value that P minus V A cube, P minus V equals to V B cube by A cube. So we got the result in this way. We can write P equals to V B cube by A cube plus 1. So we got the shear force equals to P A cube by B cube. Isn't it? Yeah, shear force of P A cube by A cube plus B cube. Now we have to say what is the value of theta 1 and value of theta 2. So we can write theta 1. let's say this was your theta 1 and this one is your that theta 2. So theta 1 is your p minus v, that's pl square by 2ei, and we know that value of v equals to p a cube by a cube plus p cube, and you have a square by 2ei, and you solve it, you get the value equals to pb cube by a cube plus b cube and a square by 2ei, and similarly you can get the theta 2. Say theta 2 equals to vb square by 2ei. That value of shear force here is shear force v equals to pa cube by a cube plus b cube, then you have b square by 2ei. So if you want to make that, let's say a equals to b, for a equals to b, we can get the value. We can get the values of theta 1 and theta 2. Let's say a equals to b. We can write here. If a equals to b, we can write a implies theta 1. Theta 1 is equals to, let's take all in terms of a. We can write a to the power 5 divided by 2 times a to the power 3 by 2 ei. We get the value as pa square by 4 ei. And in this case, we can write pa to the power 5 by a cube twice and 2 ei, and we can get the value of pa square by 4 ei. So we got this one. Next one is your that we can have. See, we can't sum them. We can't sum them because this one is rotating independently and this one is also rotating independently. You can't do summation of these. See, this one is acting in the clockwise and this one is acting anti-clockwise. Okay, we can have next one. Let's say you have same beam and same supports and same hinge. You have same hinge, but loading is UDL, and this is your A, this is B. We can have that. For this case, we know that moment won't be there at the hinge. Bending moment is 0 at the hinge. If you say there is no load acting on the hinge, we can say there is some shear force V, here's some shear force V, then same shear force gets transferred here, downwards V, and in this one upwards V, upward V. So this is your A, this is your B, and you also got loading. We know that delta 1 equals to delta 2, by the compatibility of that hinge. So it gets downwards. So if we write both are acting downwards, V is also downwards and your W is also downwards, so they get added up. So we can write VA cube by 3ei plus WA to the power 4 by 8ei. That equals to your shear force is upwards, so we can write minus VB cube by 3ei and plus this one is acting downwards, so we can write WB to the power 4 by 8ei. So we can add the shear forces in one side. We can write V A cube plus B cube by 3ei, and we equate this one WB. We can write W by 8ei common, B to the power 4 minus A to the power 4. Is it correct? Yeah. So we got the value of shear force equals to loading intensity 3 by 8 and B to the power 4 minus A to the power 4 by A cube plus B cube. That you got. let's say that your v equals to, let's say that a equals to b at a equals to b. If you write a equals to b, we can say if a equals to b, that means this becomes 0, so your shear force becomes 0. If a equals to b, that means if the loading is such that you have UDL, you have hinge here, this is 5 meter, this is 5 meter, there is only effect of this one, so it will go deflected by some amount of delta 1, and this one is also getting by same amount of delta 1, that is equal to WL to the power 4 by 80i, and it has a some value of theta 1, and this one is also having theta 1. We can say theta 1 is equals to theta 2, because loading is same, length is same, so your theta is also same because your loading is acting, and we say that shear force becomes 0, so your theta 1 equals to theta 2 in this case. So if you want to say what was the value of slope here was WL to the power 4, WL to the power 3 by 6 EI, and plus VA square by 2 EI. And in the next one, this was your theta 1. It was acting clockwise, and your theta 1 was, theta 2 was downwards. Let's say this was anti-clockwise, theta 2. So theta 2 is having two components. One was your loading downwards, because of that theta was anti-clockwise, theta 2 dash, and we have also one more, that shear force was acting upwards. So because of that, if you want to say the theta was clockwise, so we can write theta 2 double dash. So then we have to add them. So theta 2, we can write theta 2 dash was equals to WB cube by 6 EI, and this one was equals to shear force VB square by 2 EI. Then you equate this one with this one. No, we don't have to equate this one. We know that this one is a theta 2 and this one is a theta 1. If there was some shear force, the shear force was possible if shear force was not 0 at the rate of A equals to not equals to B. If A was not equals to B, then means your shear force was there. If shear force was there, that means theta 1 was there and theta 2 was there, and theta 1 was not equals to theta 2. Now we have one more problem. Say you got now a guided roller. We call it a guided roller. This one is your guided roller. Say your loading intensity is W, UDL for length L. You have the property of guided roller that it offers restraint in say in this direction, where perpendicular to the it offers restraint perpendicular to the direction in which it can move, in which it can offer moment, in which it can offer moment, not moment, and it offers a moment also. There is some moment also M. So this is the property. Let's say that guided roller was installed in this way. So then the reaction would have been this one and some moment M, but it can go in this direction. Here the reaction here is 0, horizontal. Here the vertical reaction is 0 in this one. This one is 0. So we have the compatibility condition. Compatibility condition says that theta at, say this is your support B, theta at B equals to 0. So we can superimpose the effects. Let's say because there was no roller or guided roller, and there was only UDL acting, so the theta here developed was a clockwise theta of WL to the power 3 by 6 EI, and because of that moment, there should be some moment. Say to lift that upwards, we have to apply a moment such that it deflects upwards. So if we apply a moment such that this acting clockwise. If the moment is acting clockwise, it would deflect more downwards. So there should be some moment that's acting upwards. So an anti-clockwise moment should be there. If an anti-clockwise moment is there, you can rotate it such that the theta, you can rotate it upwards such that theta final becomes 0. So there should be some value of moment upwards. Okay, right, moment has to be upwards at the guided roller. This is the reaction developed at the guided roller. So it gets upwards. Let's say the theta here is anti-clockwise theta. Here it was clockwise theta. So we can write theta equals to ml square ml by ei. So we can get the value of, we know that theta, that compatibility, that theta 1, that theta is 0, which implies this one was your clockwise, this one is your anti-clockwise, which implies net has to be equals to 0. We can write the moment developed equals to WL by 6, WL square by 6. So this is also a conclusion that if the URL is acting, how much moment is getting developed at the guided roller. WL square by 6. WL square by 6. Where we have reached? The page where I left it. Yeah, we have reached here. So we got the value of that theta. We got the value of that moment, but there would be some delta in the y-axis. So there would be some value of delta. If you want to say what is the value of delta net, this was your roller, guided roller. Because of the loading, it would go deflect downwards, but it would maintain the slope that theta should be 0. If theta was here 0, here it's also 0, but it can go deflected downwards by an amount of delta net. We have to calculate that. So we can say because of only UDL was acting, if say UDL was only acting, so this was your delta 1, and because moment has created in the opposite direction, that is your delta 2. So we can write delta 1 minus delta 2. So we can write delta 1 is your WL to the power 4 by 8 EI, and your moment ml cube by ml square by 2 EI, and value of m equals to WL square by 6. So we can get the value of delta net, that comes out to be equals to WL to the power 4 by 24 EI. That is